So, hi everyone, welcome to Ground Zero AI. We are in week 4 of NLP and today is day 2. So, in this today's agenda, we'll be looking onto two topics. First is coreference resolution, and the second one is recurrent neural networks. So, let's dive into coreference resolution first. We'll be looking into what basic description is, and then be moving on to its applications and some key concepts, right? So, it is just the task of identifying when two or more expressions in a text refer to the same entity, right? So it's essential for understanding context, resolving ambiguities, or building up systems that can understand language at a deeper level. Here I have taken an example where it's mentioned that John bought a BMW and he loves it. So it's important for the machine to understand who is he and what does it refers to. And it's also important why we mention he and it here. Why it can't be John bought a BMW and John loves it. So like if like I have just read it, but it feels a bit ambiguous, right? Because we don't want to use multiple words of the same type, right? Or like John bought a BMW and John loves BMW is very ambiguous thing, and we try to keep it short and simple as much possible. And most important is to make it a natural language, how we actually talk in a normal day, right? And that is why we also want our machine to train on these data as well. So basically, the question is who is E and what does it refers to, and that is what coreference resolution answers. So it should have many applications. It could be text summarization. So here we have understanding of key entities to avoid repetitive references. Like here we are using he for John and it for BMW. It could be question answering as well, where we resolve pronouns in questions and answers. It could be dialogue systems, where we maintain context in where there's condition for multi-turn conversation. It could be machine translation as well, where we correctly resolve preference for coherent translation, right? Thanks. Now let's talk about some of the key concepts in coreference resolution. So we'll be looking into three such main concepts here. The first one is mention. So mention is basically any noun, phrase, or pronoun in the text that could refer to an entity. So here in this example where we have mentioned John bought a BMW and he loves it. So here we have mentions like John, a BMW is also mentioned, he, it. So I think we have got the idea. Basically, we are just referring nouns or pronouns in this sentence, and that is just a mention. Next would be an entity. So entity is basically the real world object or concept referred to by mentions. So in this example, uh, John, I think I've talked about it but earlier, John and he. So these are actually same entities, right? And it is referring to John only. So this is just an entity, and also next entity could be a BMW and it, because they are referring to the same thing. It's just a mutual relationship between them. Next mention could be anaphora. So anaphora is basically a mention that refers back to another mention. So let's take an example in this. So an example here can be the child is crying, he is hungry. So here he is referring to the child, right? So this is our anaphora. Next is cataphora. So in cataphora, we mentioned mention refers to another mention that appears later in the text. So if we take an example that when he arrived, John was tired. So here he is referring to the John, right? So when we say when he arrived, observe that he comes first, and then we say John was arrived. So basically, we are mentioning something that appears later in the sentence because he is referring to someone who was waiting for John, but John was tired. So it basically refers to another mention that appears later in the text. Cool. So I think this is clear up to this point. Let's look on to some types of coreference resolution. So the first type is basically pronoun resolution. So in pronoun resolution, we resolve pronouns, maybe like he, she, or it to their corresponding entities. So suppose we take an example like Alicia said she would come. So here she refers to Alicia, right? So this is our pronoun resolution. Next is nominal coreference. So in nominal coreference, we resolve noun phrases to entitles. So if you say the doctor entered and the physician looked worried. So here the doctor and the physician are referring to the same individual. Yeah, basically the entity is the same. So here this is the condition for normal coreference. And the third type is proper name reference. So here we resolve proper names referring to the same entity. So if you say Barack Obama is the 44th president and Obama was elected twice. So here both as these are proper nouns, right? So we are referring to the same entity. So this is the condition for proper name coreference. So I guess we are pretty much clear about coreference resolution, and you can explore more about it. You'll be given an exercise, and please do attempt quizzes as well to give it a more idea about what coreference resolution and whatever we are actually studying here. So let's next start RNNs, and believe me, RNNs are the crux or the very much foundation of all transformer and whatever we are seeing today, because it was RNN only which has some problems. That why the transformer architecture actually evolved. So let's start with RNN in this study software. Let's focus on RNN. Right. So we need to first understand what RNN basically is. So it is just a neural network that is specialized for processing a sequence of data. So what basically you'll say like what basically a sequence is. So sequential data basically are like text or time series or audio where the input order actually matters. So this is why we are exploring RNN, that is solving this problem of sequential input data. And the core idea here is basically RNNs process sequences one step at a time. So like they retain information about previous steps through hidden states. So we are looking into some of the variations in sequences and what possible sequences we could have. So here, if you see, we have two such figures, rectangles and arrows, right? So here, each rectangle is sort of vector, and arrows represent, functions. Like the function could be, a matrix multiplication or addition. So input vectors, we are showing in red, and output vectors in blue, and the green vectors, they are just holding the RNN state, like what we call them hidden state. So the first one, if you see here, if we mark this as 1, right? So this is purely vanilla mode of processing without any RNN. So here, like from fixed size input to very fixed size output. uh, Basic example could be image classification. Second is, you know uh, it's a sequence output. Basically, if we say like in image captioning, that takes an image and outputs a sentence of words, and from one we could have many such outputs. Third is many to one, and here we have a sequence of inputs, right? Example could be sentiment analysis, where a given sentence is classified as expressive, could be positive or negative or neutral. Fourth could be many to many. Here we have a sequence of input and sequence output. Example could be machine translation, where an RNN reads the sentence in English and then outputs a sentence in Spanish. So yeah, this is going to be many to many. We have multiple words, input or output. Next is again many to many, but here we have synced sequence and output, input and output. So example could be where we video classification, where we have multiple frames, right? Like when we wish to label each frame of the video. So yeah, this is the what possible sequences we can have possible, or we can have the possibility of. Cool. Let's build up some more context here. So let's say uh, in any NLP problem, let's say in any NLP problem, uh, if we want to predict the next word in any sentence, it is important to know the words before it. And recurrent neural networks are called recurrent because they perform the same task for every element of a sequence without the output being dependent on the previous computations. So, but another way of thinking about RNN is that they have a memory which captures information about what has been calculated so far. So, it's better to understand its architecture. So, we'll be diving more in RNN's architecture now. So, I have took reference of deeplearningbook.org book for this diagram. And yeah, let's dive into governance architecture. So basically, this side of left side of this diagram shows a notation of an RNN, and on the right side we have this same RNN we unrolled, or we have just unfolded it into this full network. So by unrolling, we mean that we write out the network for the complete sequence. So for example, if the sequence we care about is a sentence of, 4 or 5 words, so the network would be unrolled uh, up to 3-layer network for 4 words, or to 4-layer network for 5 words, 1 layer for each word actually. So here the first is input. So input here, you say this xt. So this is just taken as the input to the network at time step t. So here, for example, we have, let's say, x1. That could be a one hot vector corresponding to just a word of a sentence. Yeah, next is h. So what h is basically? It's a hidden state, or it represent a like state at time t that act as memory of the network. So here HT is basically calculated based on the current input and the previous time steps hidden state. So for this HT, if you say for this HT, right? So this will be calculated based on the current input. We have this current input, right? We have for this HT, we have this current input and the previous state, previous time state hidden state. So basically this thing, right? This thing. So for this HT, we have this state put and yeah, previous states hidden state. So the function here would be, let's see. So this is the function here for this execution, and it's defining the same thing. For this hidden state, we have current state input and previous states hidden state input, right? So here the function f is basically taken to be a non-linear transformation, could be some ReLU function or tanh function. So this is about hidden state, and next we have weights, right? This is weight, and in weights the RNN has input to hidden connections parameterized by a weight matrix that could be W or U. So here hidden to hidden recurrent connections that are parameterized by a weight matrix W, and hidden to output connections, right? Parameterized by a weight matrix V, right? So, and all these weights, what mentioned these weights as well, U, V, and W. All these are mentioned here from input, from from the state, hidden state, and for W as well, of like between two hidden states. So here, they are shared across time, right? And next we have output, OT, which is basically the output of the network. So in this figure, we just put an arrow, after output here, basically this thing, which is also often subjected to non-linearity. So especially when the network contains, further layers of downstream. So this is just basic architecture of RNN network. Cool. So we'll be looking into three main steps in RNN implementation. First is forward pass, second would be backward pass, and third is we'll be computing gradients. So normal, what neural network computation look like. So we'll be again proceeding with that approach. So let's start with forward pass. So I have taken this reference of equation from the same book. So here, uh, for an RNN, the computations are performed sequentially across time steps, like 1 to up till time t. So the equations from this image, like they are described for a single time step t, and let's define them one by one. So we have a hidden state activation, right? This thing, and this is basically, what we are doing is basically we have a b is basically a bystem for the hidden state, and w here, w is the weight matrix that contains the hidden state at the previous, like that is at t minus 1 time to the current time step t. And next we have capital U, like it's a weight matrix connecting the input, current input xt to the hidden layer. Next we have, you know also we define ht minus 1 in this state. So this is the hidden state from the previous time step. And now the last we have xt is basically the input vector at the current time step. So this step, aggregates information from the current input and the previous hidden state. And now next we have hidden state update. This is basically ht, and this is, here we have an activation function, uh, at, that is passed through a tanh function which compresses values between, so of tanh actually compress values between minus 1 1, and for ReLU we have 0 to max, right? And that is about, activation functions. So this tanh function actually ensures stability with this compression. And next we have, output activation, ot, that we have the C is basically the bias term for the output layer, and we have capital V, which is weight matrix connecting the hidden state to the output layer. We have just this thing, right? This is the V talking about. Cool. And we have HT also, that is current hidden state. And at last we have YT. So YT is nothing but uh, an output prediction, that is basically softmax of OT. So here we apply softmax function to the output OT to, generate probabilities for different classes in a classification task. It's some sub to like one, it's at the highest. And next, let's study about backward prop. So let's talk about backward propagation. So in the case of RNN, we say it, BPTG. That is backward propagation through time, because we have a sequence of time, right, in RNN. Like we say time steps starting from 1 to up till time t. So the backward props computes gradients of the loss with respect to the weights. As you see, like we have certain weights here, U, V, W, right? And for we also take the bias as well, B and C. So by propagating errors backward through time, since RNNs deal with sequential data, the error from one time step depend on future time steps as well. So here we have certain steps. Let's go step by step to do the backward probe. The first one is to define loss function. Loss function. So the total loss is the, sum of losses across all time steps. So I can't actually formulate it here, but here we define as we have L1, L2 up till LT losses, and we just do a summation over it where, these LTs are the loss at time step T. It could be cross entropy loss or classification task. Next is gradient of output, that is OT, right? This thing basically. I'm talking about this thing. So here we compute the error at the output layer. So this process is as same as what we do in normal backward propagation for a neural network. So we compute the error, at output layer. That is, some delta at time t is equal to y predicted minus y. What is actual? So this, so it could be a true label, that is one hot vector, and other is the predictive probability for. So next is uh, gradient for V that are output weights and by C, right? So again, we compute the same del L by del V, and next we do partial derivative actually, right? So del L by del C as well. So again, we are computing gradients, and then we do back propagation to hidden state, where the error propagates back from the output to the hidden state, and this back to hidden state. And next we do gradient for hidden bits that are basically W, U, B, right? So, so for W, we do hidden to hidden. These are basically hidden to hidden bits, right? You see this W. W is basically hidden to hidden bits. U is basically input to hidden bits, and B is the hidden state, hidden bias. Sorry. So this is normal backward propagation, and we also computed the gradients here. And in on the server, we'll be providing all these equations, which are actually incorporated in these formulations. Please just go through it and try to understand from here. If you have like certain doubts, just ping just ping there, and someone will answer there. Cool. So let's just quickly discuss some of the challenges in the system of RNNs. I think it's just been here. I think you have pretty much guessed it. The first one is vanishing gradients. So this is actually during propagation, gradients can shrink exponentially as they are, propagated through many time steps, leading to negligible updates to earlier layers. One problem could be like this makes it hard for an RNNs to learn long-term dependencies, and this is one of the disadvantages that's why we have transformers architecture now. And one problem is exploding gradients. So gradients can grow exponentially sometimes. That leads to instability, and it also could lead to mitigation as well, where gradient clipping happens, like that limit the gradient magnitude. So these are some of the challenges in this approach. I think this is clear up till now. And to summarize this, what we first did is was a forward pass that compute the hidden state and output sequentially for all time step in this RNN network. Next is backward pass, where we propagate errors backward through time to compute gradients. And also we discuss some of these challenges like vanishing and exploding gradients that make training difficult for long sequences. So yeah, this is pretty much summary about RNN. Your next task should be looking open to those equations we'll be sharing with you of these processes, which is happening in backprop or like computing gradients and doing a from scratch implementation of this RNN. Like we'll surely be sharing a practice notebook with you. So this is all for this session. In the next session, we'll be discussing LSTM, GRU, and next sequence to sequence model as well. So yeah, please do subscribe to this channel and practice these problems, right? What the processes has been involved in the RNN implementation. And yeah, let's meet in the next session. Thank you for watching.